While the planets get a lot of the attention in school and by space agencies, there are smaller, less known worlds in our solar system that are just as interesting. 4 of them are known as the Galilean moons, Jupiter's 4 largest moons. Considering they are so close together, they are fascinating because they are so different. You have a volcano moon, a moon that has one of the best chances of containing life out of anywhere else that we know of, the biggest moon in the solar system, and an ancient, scarred moon whose surface can be traced back to the solar system's very beginning. I'm Alex McColgan and you're watching Astrum, and in this video we will go through these special worlds one by one and do a deep dive into what makes each one so unique. By the end of this video, I'm sure you'll understand why they will be the subject of 2 missions this decade from both NASA and ESA. We'll start with the innermost moon, Io. Let's get to know the context of Io a little better. Jupiter has 79 moons that we know of so far. There's a few that orbit close to the planet in and around the planet's rings. Beyond that are 4 large moons known as the Galilean moons, named after Galileo who discovered them in 1610. From innermost to outermost, these moons are Io, Europa, Ganymede and Callisto. Beyond them are the irregular moons of Jupiter, all of which are much further out than the previous moons. Io orbits very close to Jupiter, only 350,000 kilometers above Jupiter's cloud tops. This means from Io's surface, Jupiter would appear 39 times bigger in the sky than our moon. Io orbits Jupiter in only 42.5 hours compared to our moon's monthly orbit. At some points in its orbit, the tidal bulge on Io is thought to be up to 100 meters. This effect is similar to what we see on Earth with the ocean's tides being caused by the moon, although on Earth the effect is much more minimal, the tides only usually shifting about 2 meters from high to low. Io is getting 300% more tidal force exerted on it in comparison to our moon on us because of its close proximity to the biggest planet in the solar system, Jupiter, and the other big moons in the system don't allow the moon's orbit to be any less eccentric, meaning Io isn't going to be getting any respite anytime soon. A day on Io is the same as its orbital rotation, which means that Io is tidally locked to Jupiter. Just like we can only see one face of our moon from Earth, only one face of Io can ever be seen from Jupiter. Io is a pretty big moon, although it is the second smallest out of the Galilean moons. It is comparable in size to Earth's moon and shares a similar density, meaning it has a similar amount of gravity. But interestingly, it does have the highest density of any other moon in the solar system, one of its many unique features. Another is that it is composed of mainly silicate rock and iron, similar to the terrestrial planets and our moon. In comparison to most other big moons in the solar system, which are made of water ice and silicates. Io in fact has the least amount of water of any known body in the solar system. Its core is likely to be made of iron or iron sulfides, surrounded by a silicate-rich mantle and crust. The core is not thought to be convecting though, as no magnetosphere has been detected around the moon. The mantle is thought to be liquid near the crust, and is at least 50 kilometers thick. This is where all the volcanism originates. Which brings us to perhaps the most interesting part about Io, the hundreds of huge volcanoes all over its surface. Before the 1970s, we didn't know much about Io at all, although telescopes were starting to pick up hints that the moon was devoid of water and that it may have a surface of sulfur. The first mission to see Io in any kind of detail was Pioneer 11, although the quality was still not great. What it did detect, however, is that Io was made of silicate rock and not water ice, and that it has a thin atmosphere. Pioneer 10 was also meant to take some close-up shots of Io, but this was lost due to Jupiter's radiation interfering with the onboard command system. The radiation Pioneer 10 went through was 10,000 times stronger than the maximum radiation around the Earth. The next missions to Jupiter were the Voyager 1 and 2 missions in 1979. Voyager 1 flew by at a distance of only 20,000 kilometers and was able to take some impressive close-ups of Io's surface. What it saw was a remarkable landscape full of vibrant colors and a total absence of impact craters. It found mountains taller than Everest, as well as volcanic pits hundreds of kilometers wide, and what looked to be lava flows. Most notably, however, was the presence of plumes coming from the surface. This proved that Io is volcanically active, and it is still the first and only place this has been visibly seen beyond Earth, not including cryovolcanoes. Voyager 1 also confirmed that the surface of Io is covered in different sulfur frosts. This is what gives Io its many spectacular colors. It found that it is these sulfur compounds that dominate the atmosphere. Voyager 2 also saw Io in July of 1979, but was much further away at 1 million kilometers, although it still saw 7 of the 9 plumes Voyager 1 saw in March, which meant those volcanoes had likely remained active throughout those 4 months. The really interesting images came about with the Galileo spacecraft that arrived at Jupiter in 1995. The spacecraft wasn't especially designed to study Io, but it was able to acquire some of the highest resolution images we now have of its surface. Sadly though, Galileo never worked at full capacity, as it had quite a few mechanical malfunctions, which means we could have had even better images had it been fully operational. What it was able to see though were plumes from many volcanoes, as well as confirming the volcanoes were erupting sulfur and silicate magmas, similar to what we have on Earth, except the magma on Io is also rich in magnesium. The surface of Io is spectacularly colourful. The yellow plains are composed of mainly sulfur. The white areas are mainly fresh sulfur dioxide frosts. Towards the poles, the sulfur is damaged by radiation, which can be seen as the poles appear redder than the rest of the planet. In other places, the colours of red are the deposits left by volcanic plumes that reached hundreds of kilometres above Io. The most obvious deposit is from the volcano Pele. Sadly, an inactive volcano when Galileo was around, but Voyager 1 was able to see a massive plume when it passed by. In this image, this plume is 300 kilometers tall and 1,200 kilometers wide. In other words, roughly the size of Alaska. Interestingly though, the source of lava flows on Earth are typically the depression you would normally see at the top of volcanoes. But these depressions are not found on high peaks on Io. Instead, you have these lava lakes with high walls along the outside. Here is Loki, the largest volcano depression on Io, 200 kilometers in diameter. These lakes are directly connected to the lava reservoir below, but usually have a thin layer of solidified crust on top. On average, Loki produces 25% of the average heat output of Io, but sometimes the crust on the lava lake sinks back into the lake, causing Loki to produce 10 times more heat than normal. This can especially be seen in one of Io's other big volcanoes, Tvashtar. Normally this area looks like this, but here the crust is seen falling into the lava lake. In this image where there is just white, the radiant energy from the lava curtain was so intense that the camera only registered white. In 2007, New Horizons used Jupiter as a gravity assist on its way to Pluto. It also used the opportunity to test its equipment. It focused its lens on Io during its flyby, and what it saw was amazing. Tvashtar, the volcano I just mentioned, was in full eruption, and the plume could be seen hundreds of kilometers above Io's surface. You can also see smaller eruptions around the moon. I must admit this is one of the most impressive things I've ever seen of space. Even though the volcanoes tend to be flat, it also has some extremely tall mountains, the highest one reaching 18 kilometers tall. These mountains tend to be completely by themselves, not as part of a ridge or a range. Although most are not volcanoes, lava lakes are found near them, indicating there are faults in the crust near these mountains. Another of the unique aspects of Io is its interaction with the magnetic field of Jupiter. Jupiter has an extremely large and strong magnetic field, and Io orbits within some of the strongest sections. The unusual thing about this interaction is that when particles from some of Io's thin atmosphere and its eruptions are lost to space, these particles float in orbit around Jupiter in what is known as a neutral cloud. This cloud can extend far beyond and behind the orbit of Io, but also surrounding Jupiter is something known as a plasma torus, a donut of ionized particles that follows the rotation of Jupiter's magnetic field. The plasma torus rotates a lot faster than Io's orbit, at 70 kilometers a second compared to Io's 17 kilometers a second orbital velocity. Io orbits right through the middle of it, with the particles from the torus bombarding the particles in the neutral cloud, exciting them to higher energies. These newly ionized particles feed into the torus, attracted by the magnetic field lines of the magnetosphere. These particles are lost from the neutral cloud into the plasma torus at a rate of about 1 ton of matter per second, which greatly increases the size of Jupiter's magnetic field. In fact, if it was visible, Jupiter's magnetosphere would be about the same size as the Moon in our sky. Io's interaction with Jupiter doesn't end there. Jupiter's magnetic field lines, which Io crosses, couple Io's atmosphere and neutral cloud to Jupiter's polar upper atmosphere by generating an electric current known as the Io flux tube. A flux tube is basically a concentration of magnetic field lines. The Sun has these between sunspots and is very visible on the Sun because of the charged plasma that flows between them. Io's flux tube causes an aurora trail around Jupiter's poles. This point here is the flux tube from Io striking the upper atmosphere of Jupiter. Aurora are also visible on Io, although they are not just limited to the poles. The different colors represent the different particles being ionized. Green is sodium, red is oxygen, and blue from sulfur. Europa, one of the most exciting moons in the entire solar system. It is a beautiful world filled with mysteries. This is the first ever close-up image of Europa, taken by the Pioneer probe back in 1973. Since then, we've had the Voyager and Galileo probes explore the moon, and with each visit, Europa has never failed to surprise us. We are yet to solve a lot of Europa's puzzles, but there are many things that we are starting to piece together. Let's first of all see where Europa fits into the Jovian system. Europa is the second and smallest of the 4 Galilean moons, although it's still the 6th biggest moon in the entire solar system, just behind Earth's moon, with a diameter of about 3,000 kilometers. It takes Europa 3.5 days to orbit Jupiter once. Interestingly, the first 3 Galilean moons, Io, Europa, and Ganymede, are locked in a 4-2-1 orbital resonance due to their gravitational influence with each other. This orbital resonance and the constant gravitational tugging from the other moons keeps the orbit of Europa from ever becoming completely circular. Due to Europa's slight ecliptical orbit, the magnitude of the gravitational force acting on it from Jupiter increases and decreases as it orbits. This creates tides that stretch the moon's surface. These forces are significant as they have a big influence on the moon's appearance and what goes on under the surface. Europa's surface is made predominantly of water ice. As you can tell, it looks very remarkable and distinctive due to these long, continuous fractures and cracks. These are called lineae, which translates to lines in Latin. These lineae are often only about 1 to 2 kilometers wide but can extend for thousands of kilometers across the moon's surface. We aren't sure how or why these linea are formed at present, but the most likely theory is that as the crust pulls apart from tidal flexing, warmer material from beneath fills the gap, in a similar fashion to the ocean ridges on Earth. In this image taken by the Galileo spacecraft, you will notice some dark brown spots. They are very small, only about 10 kilometers across, and they are known as lenticulae. They are also believed to be formed by the upwelling of hot, less dense material to the surface, either by pushing the existing crust up or by breaking through altogether. Should the underground material have broken through, what we can then see are these strange, unusual terrains called chaos terrains. They are really rough patches surrounded by a rather smooth surface. These spots are expected to be soft and may contain significant information about what's under Europa's surface, which we will get to later in the video. Data from Galileo also indicated that Europa's equator may be covered in icy spikes called penitentes. These vertical cracks may be up to 15 meters high and will have formed from direct overhead sunlight on the equator. Interestingly, penitentes are found on Earth too, in dry regions at high altitudes, although nowhere near as large as on Europa. Despite being roughly the age of the solar system, Europa barely has any craters. Europa has less than 50 major craters, whereas the Earth's moon has more than 5,000 craters with a diameter above 25 kilometers. This indicates that Europa's surface is constantly changing and reforming. Models suggest that Europa's surface is only about 30 to 180 million years old, which is very young in geological terms. Additionally, Europa's icy surface is the smoothest surface of any known solid celestial object in the entire solar system. Its icy crust also has an albedo or light reflectivity of 0.64, one of the highest of all the moons. Europa's albedo makes it 5 times brighter than our moon. The surface is bombarded by a constant and intense blast of radiation from Jupiter. The radiation level at the surface of Europa is equivalent to a dose of about 5,400 millisieverts per day. Exposure to radiation at that level would be enough to kill a human in a single day. The reddish-brown color spread across the cracks and fractures of the moon is believed to be due to salt and sulfur compounds mixing with water ice and then modified by Jupiter's radiation. A recent study from JPL suggests that Europa might even glow in the dark. Energetic ions from the radiation penetrates the surface, which would energize the molecules beneath, which would make them release energy as visible light. Unfortunately, we cannot see Europa's dark side from Earth, as we are between it and the Sun always. So we are going to have to wait for future missions to Europa before we can prove this. Radiation received from Jupiter plays a significant role in Europa's atmosphere as well. Europa has a very tenuous atmosphere, composed primarily of oxygen. Unlike on Earth, the oxygen on Europa is formed by radiolysis, or in other words, the process of radiation bombarding the water ice surface, separating the H2O into oxygen and hydrogen. Hydrogen escapes Europa's gravity altogether because it's so light, whereas a lot of the heavier molecular oxygen remains. The hydrogen and oxygen that escape Europa's gravity form a dispersed neutral cloud, which follows the orbit of Europa around Jupiter. In 2012, the Hubble Space Telescope discovered plumes of water vapor erupting from Europa's south pole. This image suggests that the water plumes rise up to 200 kilometers from its surface. In 2018, astronomers found additional evidence of water plume activity on Europa when they looked back at the old Galileo data with a new data analysis technique. A dedicated mission studying these plumes can also help us understand what's inside the moon without having to land on it. Because what may lie underneath that solid ice surface is perhaps the most fascinating thing about Europa. There is likely to be a global ocean between a rocky mantle and the water ice crust. The first clue that this amazing ocean world was hidden under its surface
was provided by the Voyager and Galileo probes in 1979 and the late 1990s respectively. Between these missions, there was a drastic change in the magnetic field of the moon, which is not possible unless there is some electrically conductive fluid beneath its surface. Europa's crust also indicates the presence of a liquid layer beneath it, as it rotates with an angle of 80 degrees, which is not possible if the crust and rocky mantle were mechanically attached. Instead, it is likely that the icy crust floats on the ocean, and it is believed to make one full rotation around the moon once every 12,000 years. The fact that this ocean is not attached also explains the multitude of lineae on the surface. Tidal flexing should cause lineae to form at specific points on Europa, not all over. However, because the position of the crust changes over time, and one spot never stays in the same place for long, hence why more and more lineae form. Europa is 780 million kilometers away from the Sun, which is 5 times further away than the Earth. That makes the sunlight about 25 times fainter here. As such, Europa, or any other moon in the Jovian system for that matter, barely receives any heat from the sun. So unsurprisingly, it's cold enough here that the surface is frozen. In fact, Europa's surface temperature averages about minus 160 degrees Celsius at the equator and minus 220 degrees Celsius at the poles, keeping Europa's icy crust as hard as granite. However, tidal pressures exerted on the moon as it orbits Jupiter heats Europa's core, so geothermal activity from the core should keep the subsurface ocean in a liquid state. This ocean is believed to be under only 15 to 25 kilometers of solid frozen crust. The ocean itself is probably about 60 to 150 kilometers deep. Interestingly, Europa is only 1/4 the diameter of Earth, although it may contain twice as much water as all of Earth's oceans combined. What's most interesting about Europa's ocean is that scientists believe that it is in contact with Europa's silicate rocky mantle. This makes Europa's ocean a suitable environment for life as we know it to exist. We believe that life requires water, minerals, and energy to form, and Europa seems to have all these requirements. From the evidence we've seen so far, scientists are extremely confident that this ocean not only exists, but that chemical reactions can take place there, and that there is enough tidal energy heating the core that geothermal activity may exist on this ocean's floor. As we have seen on Earth, whole ecosystems can exist in such places, far from the sun's light. So for now, Europa is one of the most likely places we can find life outside of Earth. Now, NASA's Europa Clipper spacecraft is scheduled to launch in 2022 and is likely to reach the moon by the end of the decade. It is scheduled to perform more than 42 flybys of Europa. ESA is also working on their own spacecraft called JUICE, or Jupiter Icy Moons Explorer, which will explore Jupiter and 3 of its largest moons, Ganymede, Callisto, and Europa. JUICE is also scheduled to launch in 2022 and is also likely to reach the moon by the end of the decade. These probes are specifically designed to examine Europa's water plumes and atmosphere. NASA is also planning a Europa lander mission, but this mission is going to launch well after the Europa Clipper mission. These missions will help us know more about Europa and hopefully confirm the answer to the most tantalizing question of all: does it and can it sustain life? At the very least, these missions will give us a new perspective of our solar system and help us understand how it works. So there we have it, almost everything you could want to know about the fascinating world of Europa. Ganymede, the third of Jupiter's Galilean moons, the largest moon that we know of, and home to the largest water ocean in the solar system. But there's something else that sets Ganymede apart from anything else we've seen before. This Jovian giant contains an intriguing mystery buried deep beneath its surface. There are 79 different moons of Jupiter, and Ganymede is the third of a group known as the Galilean moons, Ganymede is the largest of these four, with an impressive diameter of 5,268 kilometers. For a point of comparison, this is 0.41 times the size of Earth's diameter, and 1.02 times greater than the previously thought to be largest moon, Titan. It initially appeared bigger because of its thick atmosphere, which stretches hundreds of kilometers into space. Ganymede's volume is even 26% larger than Mercury's, although it doesn't contain as much mass. Ganymede's average density is 1.9 grams per centimeter cubed, compared to Mercury's 5.4. This is because of its composition. Like Europa, Ganymede's surface is a thick crust of water ice, extending 150 kilometers deep, underneath which is believed to lie a vast ocean of liquid water. And when I say vast, it really is. Because while Mercury has very little water and is rich in dense metals, the abundance of water on Ganymede reduces its average density. The ocean of Ganymede is so big that it contains more water than all the oceans and seas on Earth, and it is estimated to be 100 kilometers in depth on average, 10 times deeper than the deepest point in our ocean. All of this water means that Ganymede is only 50% rock, the rest being water and small amounts of metals and other ices. This seems appropriate to me, as the name Ganymede comes from the classical mythology, where Zeus, or as the Romans called him, Jupiter, claimed a young boy called Ganymede and took him to be a cupbearer for the gods. It seems fitting that the moon Ganymede would also carry so much water around for Jupiter. Interestingly, Ganymede has an atmosphere that contains oxygen. Now you might be wondering, with all this water and an oxygen atmosphere, is it possible that life exists on Ganymede? While it's certainly possible, there are some features of Ganymede that make this unlikely. To begin with, the oxygen atmosphere is very thin. It is estimated to be somewhere between 0.2 to 1.2 micropascals, or about 100 billion to 500 billion times less than Earth's atmospheric pressure at sea level. That would be impossible to breathe. And while our own planet Earth has certainly demonstrated that ecosystems can flourish in the depths of oceans without sunlight to sustain it, there could be a big problem that prevents this from happening on Ganymede. This is because the ocean of Ganymede is so deep that water down at its bottom would likely be compressed back into an ice through sheer pressure. Life in the deepest parts of our ocean can survive thanks to minerals being ejected from geothermal vents. With such a thick ice layer between the core and the ocean, it is unlikely that this would occur on Ganymede. Europa, Ganymede's neighbouring moon, is considered a more likely candidate for life because of this. However, if Ganymede's ocean is salty, which there is an increasing amount of evidence for, it could change the interior makeup of Ganymede drastically. Models suggest that with a salty ocean, it could be that there are multiple layers divided by sheets of ice. If this is the case, the most internal layer could indeed be in contact with the rocky core, increasing the chances of life existing there. But underneath Ganymede's ice and water exists something else truly surprising, something that scientists do not have an explanation for. Somehow, Ganymede is producing a magnetic field. The magnetic field of Ganymede was first discovered by scientists in 1996 when the Galileo spacecraft began a series of flybys of the icy moon. The big indicator of a magnetic field is the presence of auroras, and incredibly, auroras were detected in Ganymede's tenuous atmosphere. Not only that, but as Hubble studied Ganymede over an extended period, it became clear that these auroras didn't wobble as much as expected, likely a result of something known as magnetic friction in a salty water ocean under the surface. A magnetic field is significant, as it's the feature on Earth that shelters the planet from solar radiation, enabling all life to flourish. The field around Ganymede does not completely protect it from such radiation. Being tucked within Jupiter's incredibly powerful magnetic field and radiation belt means it's still getting pelted with a lot of radiation. Ganymede's surface still has about 5 to 8 rem, enough to make a human severely ill or dead in just 2 months. But it's still better than its closer orbiting neighbour moons. Scientists are not quite sure why this magnetic field is here at all. Our planet's core is hot and molten. Convection currents within it move electrons, which in turn produces the magnetic field that surrounds us here. However, this shouldn't be happening on Ganymede. Ganymede is smaller than Earth, and given its size and composition, scientists believe that the core should have cooled down enough by now that it should be a solid mass, not liquid. This would prevent electrons moving through convection and would prevent a magnetic field. And none of the other moons of Jupiter have a magnetic field. In fact, Ganymede is the only moon in the entire solar system that has one. So what's going on? Scientists do not know for sure, but the answer might lie in Ganymede's incredible relationship with its planet and neighbouring moons, and a process known as tidal heating. Ganymede orbits around Jupiter roughly once every 7 days in an eccentric orbit. This means that at some points of its orbit, it's closer to Jupiter than at others. When an object comes under a strong gravitational force, it will stretch in the direction of that force, as mass is pulled in the direction of gravity. However, the further an object gets from the source of gravity, the more it will compress back to its original shape. As Ganymede has an eccentric orbit around Jupiter, it is constantly coming under more and then less gravity, and is constantly stretching and contracting. Have you ever pulled and stretched blue tack repeatedly in your hands before pushing it back to a ball shape? Then you might have noticed that after a while it gets surprisingly warm. This is because stretching produces friction as the material rubs up against itself. And on the scale of moons and planets, this friction adds up. A tidal force creating heat through friction is known as tidal heating. On top of that, in a process I find fascinating, Ganymede has formed an orbital resonance with two of its fellow Galilean moons, Io and Europa, in what is called a Laplace resonance. For each time Ganymede orbits Jupiter, Europa will orbit exactly twice, and Io exactly 4 times. This mathematically precise configuration has not happened by coincidence, but is evidence of the moon's gravities pulling on each other and the whole system attempting to conserve the resulting momentum. However, it means that Ganymede is constantly being pulled by its neighbour's gravity and is under a lot of gravitational stress. So perhaps tidal heating is warming up Ganymede enough that its core remains a liquid after all, helping it to continue to produce its magnetic field. Scientists do not know for sure, but it would perhaps explain why the surface of Ganymede is so interesting. You may have noticed that Ganymede's surface is split into large, dark regions that cover about 1/3 of its surface, and lighter regions that make up the other 2/3. Through examining the number of impact craters on these two sections, scientists can tell that the dark regions are actually older than the lighter ones, as they contain more craters. The lighter regions might have fewer craters, but they do contain long ridges and grooves up to 700 meters high and thousands of kilometers long. Truly an impressive sight. But again, scientists are not sure how these ridges formed. One explanation is that tidal forces stretched out the surface of the moon in an unstable period of Ganymede's ancient history. Perhaps this same tidal force could have also warmed Ganymede's core and preserved its magnetic field. Whatever its cause, the magnetosphere of Ganymede has been instrumental in helping scientists understand the composition of the moon. By measuring the areas that auroras appeared in Ganymede's atmosphere, scientists were able to confirm the existence of Ganymede's subsurface oceans, all without having set foot there. And as for the rest of Ganymede's mysteries, maybe JUICE, the Jupiter Icy Moon Explorer, will find us the answers. The ESA spacecraft is set to launch in 2022, and though it won't reach orbit around Ganymede for another 10 years after that, is to investigate the inner workings of a number of Jupiter's moons, including Ganymede. Until then, we may have to let Ganymede's mysteries remain just that, a mystery. Callisto. Despite the fact it is the 3rd largest moon that we know of, I think the majority of people would be hard pressed to say any facts about it at all. Is it just a boring world? Or do we simply not know much about it? Actually, we know more than you may first assume, and it is far from boring. Let's start with where it fits into the Jovian system. Callisto is the 3rd largest moon in the entire solar system, and it's just smaller than Mercury at 4,820 kilometers across. However, while its diameter is only 58 kilometers less than Mercury's, it is only 1/3 of the mass of the planet, meaning it's less dense and its gravity is a lot weaker. It is the second largest of the Galilean moons and orbits Jupiter much further out than the other three, taking 17 Earth days to do so at an average distance of 1.9 million kilometers. Even at this distance, it is still tidally locked with Jupiter, meaning the same side of Callisto always faces its parent planet. However, it does mean that it is not locked in an orbital resonance with the other three moons, nor do we believe that it ever was. Callisto has a very tenuous atmosphere composed of carbon dioxide and possibly oxygen too, although oxygen has never actually been detected yet. We know, however, that the atmosphere is so thin that the molecules contained within it do not collide, and theoretically the atmosphere should be stripped away by atmospheric loss processes in just 4 years. Scientists believe that Callisto's crust is replenishing the lost atmospheric particles through sublimation of carbon dioxide surface ices, evidenced by some interesting surface features. Now, the surface of Callisto is one of the most ancient in the solar system, with evidence placing it at over 4 billion years old. You'll immediately notice the speckled nature of Callisto. Its surface is completely covered with various sized impact craters, more so than any other object we've observed. In fact, it's close to saturation. Any new crater will probably just overlap another one at this point. Without any geological activity, cratering is perhaps the only process that has vastly been impacting Callisto's appearance over its lifetime. Why is Callisto's surface so old compared to a lot of other bodies in the solar system? Well, on geologically active planets like Earth, there are processes that can erase almost all evidence of past impacts. Earth has one of the least cratered surfaces in the solar system because so much happens on its surface. It has weather, water, plants, volcanism, tectonic plates, and human activity. These act together to break apart, wear down, and lift up the ground. Even other Jovian moons like Europa or Io have comparatively fewer craters thanks to tidal forces, which cause geological activity on their surfaces. This doesn't happen with Callisto. Callisto does not show any signs of geological processes such as volcanism or plate tectonics, and so its surface has remained intact after all these years. Limited tidal forces and thus no geological activity impact Callisto in another very unique way. There are no mountains to speak of on its entire surface. When Callisto initially formed at the very beginning of the solar system, it was likely an ocean world that has since frozen over, and apart from the bombardment of meteors, it has stayed exactly the same ever since. So let's have a look at some of these craters, because some of the biggest are truly impressive structures. This is Asgard, the second largest impact crater on Callisto, measuring 1,600 kilometers in diameter. And this is Valhalla, the largest multi-ring impact crater in the entire solar system, with a diameter of 3,800 kilometers. It's these craters that add to the unique appearance of Callisto, as they contain more rings than craters anywhere else. With these craters, the impactor was large enough that it may have completely punctured the thin crust, with it eventually refreezing over in the light patches you see in the middle. Zooming in on these middle regions, you'll notice they have a mottled appearance. There seems to be a big difference in contrast between the bright knobs and the darker plane. These regions are a lot less cratered than the rest of Callisto's surface, which would make sense if the plane truly is a refrozen surface, likely making it 2 billion years younger than the rest of Callisto. The rings are likely fractures in the crust, a concentric failure in the brittle shell of the moon. Interestingly though, within the rings, these bright knobs are still visible. So what are the knobs? Well, they are believed to be the degraded remains of the millions of crater rims from Callisto's past. We don't know exactly why they have degraded so much over time, but perhaps it's due to micrometeor impacts, or simply the ice is slowly sublimating over time. They are brighter than the lower planes because the rocky debris from the meteors and micrometeors will have fallen down the knobs over time, leaving the pure ice exposed at the top. Smaller impact craters are also fascinating due to their uniqueness. Most impact craters are shallower on Callisto compared to our moon. For instance, the Luffen impact structure. It's well over 100 kilometers wide, however, it's only 600 meters deep. This could be because the impactor was breaking apart before it impacted, causing more of a spread out shotgun effect on the surface. Or it could be that the surface has since leveled off from other, larger nearby impacts that have occurred later on. This crater is believed to be over 1 billion years old at least, yet you can still clearly see the ejecta that has streamed away from the impact, clear evidence of how unchanging this remarkable moon is. With some craters, like Haar crater, there is even a large dome found in the middle. With typical large impacts on other worlds, you will see a few concentric rings and a raised peak in the center. This is very much the case on our moon. However, Callisto has some remarkable examples of large craters where just the opposite happens. Look at Tinder here. Instead of a peak, there is actually a pit in the center. Why does Callisto have such unique craters? It could be due to the fact that Callisto's crust is not just brittle, but pretty thin too, with either soft ice or a salty ocean underneath. Estimates put the crust at 80 to 150 kilometers thick. The Galileo space probe, which spent several years around Jupiter, spent a significant chunk of its time aptly studying the Galilean moons. Galileo found that Jupiter's magnetic field could not penetrate through Callisto, implying there is a highly conductive layer under the surface at least 10 kilometers thick. This couldn't have happened in ice or silicates unless the ice layer is at least partially molten, or very large temperature gradients can be maintained below the ice to create a conductive effect. Data also suggest that Callisto has a small silicate core at its center with a radius of about 600 kilometers. Which begs the question, can Callisto be conducive to life like other icy worlds with water mantles under their surfaces? Well, life as we know it requires liquid water and energy to exist. Callisto might have an ocean of liquid water under its surface, but being about 800 million kilometers away from the Sun, it barely receives any heat from our star. And the absence of tidal forces doesn't help either, leaving radioactive elements the only source of heat to warm this subsurface ocean, if it exists. And unfortunately, even visiting Callisto won't prove anything. Moons like Europa and Enceladus have vents ejecting water directly from their subsurface oceans, meaning we can investigate habitability prospects without ever going into the oceans themselves. No such vents exist on Callisto, so scientists would have to penetrate the crust in order to find out. All these things combined mean that, unfortunately, scientists think that the environmental conditions necessary for life appear to be less favorable on Callisto than on any other icy worlds. Nevertheless, Callisto shouldn't be ignored. If we ever go to explore the outer solar system, Callisto would make a perfect base. You see, orbiting at a distance of 1.9 million kilometers from Jupiter means that Callisto is located beyond Jupiter's main radiation belt, making its environment thousands of times more conducive to human exploration than its inner moons. Callisto also has a lot of water ice that can be used for propellant production, and of course is the staple to keep humans alive. Separating the hydrogen from oxygen also leaves oxygen for breathing. Callisto's geological stability would make for building structures on the surface relatively worry-free, and the lack of huge mountains or deep trenches means it's faster, easier, and more efficient to travel over. From Callisto, we could better explore the inner Jovian system from a safe distance, or use it as a way station for heading farther into the outer solar system. Lifting off from Callisto would be ideal thanks to its low gravity, and you could get a gravity assist from a close flyby of Jupiter. It's true that this is a futuristic prospect, although if we ever do become a spacefaring species, this is a distinct possibility. Now, while Galileo did an admirable job studying Callisto during its few flybys, there is still a lot of information gaps that need to be filled. With any luck, we'll get that from the European Space Agency's Jupiter Icy Moon Explorer, due to launch in 2022, which will reach the Jovian system by 2030 and will explore Jupiter and 3 of its largest moons, Ganymede, Callisto, and Europa. ESA has planned several close flybys of Callisto during this mission. This mission might provide more insight into questions like, does it have a subsurface ocean? And if so, does it or can it sustain life? Beyond that, there's also the questions we haven't thought to ask yet. Who knows what more we will still discover about this incredible moon? So there we have it, almost everything you could want to know about the Galilean moons of Jupiter. Did you enjoy this video? Then I hope I earned your like and subscription. A big thanks to my patrons and members for supporting the channel. It really goes a long way to helping me make more videos like these in the future. If you want to support too, find the links in the description. All the best and see you next time.